Okay, so today we will talk about Henselian rings. So here is the definition. So suppose we have a local ring A with maximal ideal M, and let's say K is a residue field, is Henselian. If the following condition holds for every polynomial f of capital T, for every monic polynomial, and every alpha which is in the residue field with such that this element is 0 of my polynomial modulo the maximal ideal. And so f bar stands for the image of this polynomial in K of T. And so for every alpha which is 0, a simple 0, there exists alpha tilde in A with f of alpha tilde equal to 0 and alpha bar equal to alpha mod m. Okay? Ну, как бы один пример – это полные кольца. И тогда это лемма Гензеля, что полное кольцо Гензелева. Yes, that's equivalent, so I will explain this. And another definition is so we say that A is strictly Genselian if, in addition, the residue field is algebraically closed. Okay, so as Katya mentioned, one example of this, of Henselian ring is a complete local ring. So that's an important example. So here is, so I will give 4 more characterizations of Henselian rings. So the following conditions are equivalent. So one is, so A is going to be always a local ring. So A is Henselian. Two is what Stepan mentioned. So for every polynomial, in C, monic again, and any factorization, so f bar of T, well, as say G0 times H0. So this factorization takes place in K of T with H0 and G0 monic and relatively prime. G0 and H0 is the greatest common divisor is 1. So they generate, the ideal they generate is the entire ring that exists. Factorization GH with monic G and H, and such that G is equal to G0 modulo the maximal ideal, and H is equal to H0. Okay? So that's one condition. The third condition, equivalent condition, is the following. So it's more geometric. So for any diagram, so here I have spec A, and here I have spec B. Here I have the closed point. And I assume that this map is a tull. And this embedding admits a lift. There exists a section. Yes? So section. This is my section. So if this is pi, then pi composed with S is identity. And it's also compatible with this inclusion. So if this is I and this is I hat, then I composed with S is I hat. Okay? So every tull neighborhood of points spec K and spec A splits. So, okay. By tull neighborhood of spec K, I mean in a tull, yes, but I require this to have a lift. Okay.
Strictly in Zeland, do you need a separable closure?
So I will assume that it's algebraic. That's algebraically closed. So last time I said separably closed, but the standard terminology is algebraically closed. Sorry. So, though I think, well, so let's stick to this. Okay, this is one. And the last condition, equivalent condition, is the following. Every finite A algebra B is a product of local rings. So B is product of BI. Okay, so so A is a local algebra, right? So and B is a finitely generated, finitely generated A module, which means that B itself that the morphism from spec B to spec A is finite. And in particular, it has finitely many, spec B has finitely many B has finitely many maximal ideals. They are all over the maximal ideal in A, right? So this condition is equivalent to saying that the canonical map to maximal ideals, localization with respect to maximal ideals, is an isomorphism. Okay? This BI must be local. So that means that there are localization of B at some maximal ideals. Well, so the condition is, okay. So this, what I wanted to say is that the factorization of B inter product of local rings is canonical. It's just this map. So let me explain, give an example. Before I give a proof of this theorem, I want to give an example how to illustrate property 4. So let's first see that this 4 fails for local rings. That is, an algebra which is finite over a local ring need not be equal to product of local algebras. So, so here is an example. Let's take map from A1 to itself. And so this is spec, say, K of Z. And this is spec, okay, maybe square root of Z. Square root of Z, not to introduce too many notations, spec K of Z. So this map takes Z to Z squared. And let's consider here point, let's take localization of K of Z at point 1. So spec K of Z at 1. Oh, yeah, so sorry, I should. Что? Спасибо. Okay. So, no, I should not write. Yeah, Z minus 1, sorry. Yes. Okay, so this consists of all rational functions which are regular at point 1. And now let's take the fiber product. This is going to be my B. So the fiber product consists of, well, this map is finite, so B is finite. This is my A. So B is finite over A. And so what is B geometrically? So I want to think of B as rational functions in square root of Z. What is the condition on those rational functions? Да. Соответственно, вот получается, значит, вот у меня есть мое разветвленное вот накрытие, вот точка 1, so negative 1, 1, and so you consider functions here which are regular at these 2 points. And this is not a local ring, it has 2 maximal ideals. So this guy is and on the other hand, it's connected, right? Because it's a domain. It sits inside the field of rational functions in square root of Z. So B is not a product of local rings. Okay, so потому что B вообще нет делителя нуля. Спектр B связан. А почему в B нет делителя нуля? Потому что это подкольцо в поле. В поле рациональных функций от корня z. Хорошо? So in this case, the special fiber of this map consists of 2 points, so it's disconnected. But if I, on the other hand, if I restrict my map to Zariski open neighborhood, any Zariski open neighborhood of point 1, the fiber remains connected. Yes? So, so what is the geometric meaning of this condition here? So, so you have spec B, you have spec A, you have spec K sitting here, and you can take the fiber of spec B over spec K. So this is spec B tensor K over A, right? So maximal ideals of B, they are all, well, they are in one-to-one correspondence with maximal ideals here, right? Because every maximal ideal of B contains maximal ideal of A. Therefore, it's a maximal ideal in the quotient. So, well, this condition is equivalent to saying that connected components of this guy, this is a finite dimensional algebra over this K, right? Its connected components are in one-to-one correspondence with maximal ideals here. And the condition is that this map induces isomorphism on pi 0 on the set of connected components, right? So, for example, here you see that this guy is connected, the fiber is not connected, and even if you restrict this map to any Zariski neighborhood of point z equal 1, it's still the fiber, the pre-image still remains to be connected, right? Remains connected. So that's so interpretation of 4. So and well, another example. I will give a proof of this of the theorem in general, but let me explain that why it's easy in the case when A is complete. So as Katya mentioned, complete rings are examples of Henselian rings, so we must have 4 for complete rings. Let's prove it directly. So assume that
взять А-фактор по степени максимального идеала, то тогда вот то, что ну, оно бы распалось просто по теореме, китайской теореме Апостата. То есть это как бы на нулевое.
Да. So assume that A is complete. That's what I'm going to use now. So then B, well, B is a finite A algebra. Then B being a finitely generated modulo over complete ring, it's also complete. So B is equal to the limit of B modulo powers of maximal ideals. right? So I take the maximal ideal in A, and I generate the ideal in B. So that's the same as tensor product of B and over A with A modulo maximal power of maximal ideal, right? Because B is also complete. And so now, so these guys are infinitesimal thickenings. So you have B mod maximal ideal of B. This is a finite dimensional algebra over K. And so maximal ideals in B again correspond to maximal ideals here. And all these algebras are infinitesimal thickenings. Right? Infinitesimal thickenings. So now let's check that property. So I want to show that connected components of this are in one-to-one correspondence with connected components of B. Putting this algebraically, I want to show that idempotents here are in one-to-one correspondence with idempotents here. But definitely, this is an infinitesimal thickening. So if you think in terms of spectra, this has the same connected components, right? If one scheme is infinitesimal thickening of the other, then it has the same, the underlying topological spaces are the same. So in particular, idempotents here are the same as idempotents here. So that means that, that means that idempotents in B are in one-to-one correspondence with idempotents here. So all these connecting maps induce isomorphism on the set of idempotents. So in B, idempotents in B mod Mi. Okay. And this implied the result. So once we have factorization of this, we get factorization of B. So now let's, Henselian rings, they kind of lie in between local rings, which don't have this nice property, and complete rings. So you have more Henselian rings. Okay, so I will give, before I go to the proof, so I want to keep this on the blackboard. So I need to erase probably this. I will give one more definition. Definition. So suppose you have any A and maximal ideal. A need not be local. The Henselization of A at M is defined as the limit of called limit over the following diagrams over the following category. So you take spec A spec B, where this is a tull, and the map together with a splitting over spec K. K is the residue field. And you take a limit, call limit of B. Okay, so just a side remark is that if you replace in this condition, in this diagram here, the word etal by the word open embedding, open immersion, then you get what? Suppose I take the co-limit of B over the following category consisting of diagrams where this is an open immersion. Localization, right? So, and this should be thought as etal localization. Okay? So, exercise, which is easy from the third property, is that AH is Yanzilian. And you can also take define strict Yanzilization, A strict H, and this is also call limit now of the following diagram, spec B, spec A, and this is spec K bar, this is etal. And so this map is a composition of this one with the embedding to the algebraic closure, right? Well, equivalently, you can write it as in terms of our inverse image functor on etal sheaves. So you have spec A, you have spec geometric point, spec K bar, and call this I. Then, just by definition, this is I inverse of the structure sheaf, or spec A. And, well, I have to specify topology. So this guy also can be expressed as you take the inverse limit with respect to this map, and then you take the global sections. Okay. So here is an example. Что? Ну, у нас получается пучок на спектре К. Пучки на спектре К — это вообще-то что-то сложное. Это абелева группа с непрерывным действием К с чертой над К. Да, это уже просто абелева группа. Что значит одна и та же? Это ко-предел можно брать по диаграмму, по категории. В смысле, что я хочу, мне надо сказать, что бета меняется, но просто морфизмы. Если я эту стрелку не фиксировал, то получилась бы глупость. Горизонтальная, да. Да, я зафиксировал К чертой вообще, раз и навсегда. Да, да. Нет, К с чертой — это К — это А фактор по максимальному идеалу. К с чертой — это зафиксированное алгебраическое замыкание. Okay. So let's erase this. Now, here is an example of Yanzilization that I mentioned last time. So here is a let's see. Example. So suppose A is a DVR. And case is fraction field. Then I claim that Hensselization can be obtained as follows. You take completion of A, and you take elements in the completion which are algebraic over K. Sorry, not even algebraic, separable over K. So intersection is separable. Right? So, for example, if you take for a Z localized at one point, then you need to take elements in ZP in periodic integers that are algebraic over Q. And there are many such elements. For example, you can take square root of any element which is equal to 1 modulo B. Any integer which is equal to 1 modulo B. Has this square root exists in ZP. Сейчас. Так, тут это H. Ага. Сейчас, это отвечает на ваш вопрос или нет? Нет, а какой вопрос? Да. M. Максимальный сделан. Да. Ну да, не показываем. Не показываем. Нет. Даже если бы вы зарискали такую локализацию, то вот локализация в этих, вот мы называем это локализацией в M.
А это локальное?
Ну, не обязательно. Но это пропускается через локализацию. Можно было бы без ограничения общности считать, что А локально. Потому что гензализация А, она такая же, как гензализация локализации А в M. Потому что, в частности, в качестве всех таких, вот среди этих диаграмм есть такие, где просто это открытое вложение. И тогда это предел по таким диаграммам будет локализация. Да. Хорошо, да, это совершенно верно. Вот это отображение, оно задано M. Вот это K, это А фактор K. Вот это отображение, да, это стандартное отображение. Не какое-то, а вот именно такое. И также здесь. Okay, so let's prove this. Proof? Well, in one direction it's obvious because A.
Слушай, а если ты просто любое отображение написал, то была бы локализация в простом идеале, да?
Если бы, значит, любое, неэтальное? Нет, если бы я взял открытое вложение, то да.
Не спектр К ты вложил бы спектр А как А фактор P, а просто бы отобразил. Ну, что можно написать А отображается в фактор А по P, а А по P вкладывается в свое поле части.
Да. Okay, so because so first of all, I claim that AH sits inside. So I should have explained where I take the limit. I take the limit in where I take the intersection. This intersection is in. Do I have to explain it? I don't think so. It means this means that you just take all elements which are algebraic and separable over K. Okay, I don't care. So first I claim that that localization sits here because A is Henselian. Okay. And secondly, well, it also sits here because all these diagrams, well, they are étale. In particular, they are étale over the generic point. So it's a separable extension of the, it gives you a separable extension of the field of fractions of A. So
Да, извини, а ты просто не имеешь в виду косек, а просто с крышечкой сек имеешь в виду. Ну, как бы с крышечкой формально же не вкладывается в алгебраическое расширение.
нет, ну я мог бы вложить это следующее. Мне надо взять поле частных вот этого дела и взять сепарабельное замыкание его. Это бы там содержалось. Но мне кажется, что то, что здесь написано, имеет смысл и так. Это, еще раз, это означает, что мы берем алгебраические сепарабельные элементы с крышечкой.
Нет, ну при пополнении же у тебя же может быть пересечение максимальных. Ну в смысле не над неутром, как ладно,
Yes, so A is Noetherian. So it's A is a subring here. That was the question. Yes, because A is Noetherian, it embeds, local Noetherian embeds into A hat. Okay, and it also sits here. So really the claim is that, so this one inclusion is obvious. So what we want to show that the opposite inclusion. And so it suffices to show the following, that so I want to show that this sits here. It suffices to show that for every finite Galois extension, yeah, and this is in K-sep. So B, which is by definition L intersected with A hat, embeds into AH. So again, we think of AH already as a subring here, so this makes sense. And the proof, proof. So what do I need to show? I claim that, so if you take, so let's consider the diagram, spec B, spec A, and so here I have spec K. Now, so I claim that this map is étale. And let's check that this is étale. Well, first of all, B is finitely generated over A as an algebra. And secondly, B modulo the maximal ideal Let's compute it. Let's compute it with using this definition. So my maximal ideal is principal ideal is generated by some pi, some uniformizer pi. So what happens if I take this and take the quotient by the uniformizer pi? Well, pi is invertible here in L. So it means that that's the same as the quotient of A hat modulo pi. right? So this gives me. So that means that in this diagram, I have this map splitting over K because the fiber of this map over the closest point consists just of one point. Okay? And this point, as you see, it's isomorphic to K. So that means that this map is a tunnel. Right? Because the fiber is reduced. Well, it's not only reduced, it's geometrically reduced. It's K.
I guess if you take an extension Q into Q of I and then you try to intersect with Z5, you have two different points. And it's still like a parallel line. Why?
If you take, so you propose a counterexample. So what is your counterexample?
Let's say Gaussian integers.
What is A?
Q in Q of I.
What is A?
L is, so A is diver. A is Z localized at 5.
Z localized at 5. At 5.
Local ring.
Yes?
So L is Q of I.
L is Q of I.
Alright, you have 2 points over 5 in
Yes?
the spectrum. Why does they like collapse the 1 point?
Well, because you have to so very good point. So you take this is your A, and now what do? You take integral closure of A in L, or what? Maybe I.
It takes the intersection. I'm not quite sure.
Okay, so you take the intersection. So is I square modulo 5? Is -1 is square modulo 5?
Yes.
It is. So that means that if you take the intersection, you must get a local ring.
You have two roots. You have 2 points. One is one point plus the other.
Yes. So you take L and you take the intersection with Z5. So Z5, right? So
There are 2 different embeddings of L.
yes, but you choose one.
So under both embeddings, the
Yes.
is the same. When you
Yes.
take the limit, won't something break?
No, because
Diagram. Is it fine with embeddings?
so so the first step of the proof was to embed AH into A hat, right? And I claim that there exists such an embedding. It's not, as you said, it requires a choice. Well, it depends on maybe on. For H, it's
So we choose an extension of a discrete variation to K separable. We have to fix that for the outside.
why do we need this?
In order to have this embedded AH into A hat.
No, we don't need.
So what do we do?
So let's see why AH embeds into A hat. So let's look at the definition here. Okay. This is definition of AH. So I need to show that every B with this property maps uniquely to A hat.
It doesn't. There are choices.
No, it maps uniquely. It maps uniquely because I have this point fixed. So let's see. Да, да. Мгм. Нет, мы фиксируем вот это отображение, и оно нам все задает. Мы точку зафиксировали в B. Okay, so here I have spec A hat, and now I take the fiber product. Okay, so I have this diagram where this is spec A hat, it's Henselian, this is etal, and it follows that there exists a unique section. Why it's unique? Well, first of all, there exists a section. Any two sections, well, this map is etal, so any two sections equal on an open subset, but they are equal in spec K, and this is local. So they're equal everywhere. So there exists a unique section like this. Сейчас, ОЦП — это не качественное нормирование.
Нужно, чтобы это был тебя.
Да. Иначе пополнение не то. Okay? So now let's go to the proof.
So but it doesn't embed in key bar. So to embed this in key bar.
Bar, you need a choice, yes, but I formulated it such a way, though I wrote it as if I need this embedding. I said that it's completely canonical. Okay, so let's let me give a proof because it uses some interesting ideas. So I will erase everything. So I'm proving this theorem. Okay, so what do we start with? We start with, first I will prove that 2 implies 4. Okay. 2 implies 4. That's the longest part of the round. So I need to show that every finite algebra is product of local. So let's first assume that B is equal to is generated by one element. F monic. Okay? Then, so what do we want to show? So if F bar, so the reduction of F is a power of reducible, then B is local, right? Because then K of T mod F bar is local, right? So, and that means that this has only one maximal ideal. So if not, then we can write f bar is product of G0 and H0. So G0, H0 monic and coprime. Then we use 2. So we write F as G0, G times H, S is here. And so now I claim that they are automatic. It follows that B is isomorphic by Chinese remainder theorem to B mod F, B mod G times B mod H. So let's see why. So all I need to show is that since GH are coprime. So I need to show that in order to apply Chinese remainder theorem, I need to show that these two ideals, that G and H are coprime, so they generate the ideal generated by G and H is everything. But I know that it's true modular maximal ideal, and then by Nakayama lemma, you get that so if you have two polynomials, monic polynomials, which are coprime modular maximal ideal, they are coprime itself. So that means that we factorize B into product, so we reduce the number of maximal ideals, and by induction we can keep going. So that's okay. Now let's reduce the general case to this. So general case. Let's if B is not local, then so B mod the maximal ideal, B mod maximal ideal in A times B is also not local, but this is an Artin algebra, right? It's finite dimensional algebra over a field. So every finite dimensional algebra over a field is product of local algebras, right? Just kinetic components of the spectrum. So pick a non-trivial idempotent. B bar in B mod the maximal ideal. And then we can consider the pick any preimage of this B bar in B. So our goal is to show that this idempotent can be lifted to an idempotent in B. So for this, let's pick some any preimage of B in B So let's take, say, A of t, some f of t, B that takes where f is monic, f monic, and t goes to B here, which is equal to B bar modulo maximal ideal. So just take any preimage of B bar in B, and because it's B is finite over A, it satisfies some monic equation. Okay, you can choose this. And now I'm going to apply what we already know. Okay, so now we consider the map from C mod MAC, the reduction of this map, modulo maximal ideal, to B, modulo maximal ideal in B. So the image of this map is generated by my B bar, right? Okay, so these are Artin algebras. This is surjection. This has a non-trivial idempotent, B bar, and I can lift it to a non-trivial idempotent here, right? Because think of this map on the level of spectra. This is an embedding of a finite set into another finite set. So idempotent is just a function which is equal to 1 on a subset here, and 0 elsewhere. So you can embed it to a function of the same process of the same type on a larger set. So that means so that we have an idempotent here, B bar, and I can first lift it to an idempotent here. This is idempotent. And then this C is already of this type, right? And I know that my C is product of local rings. So that means that every idempotent can be lifted to an idempotent of C. Okay, I will write it here. So let's. That's what we proved. So now lift C bar to an idempotent C in C. And let E be its image in B. So then B is equal, so it's also an idempotent, so my B factorizes as E times B times 1 minus C, B. Okay? So using this trick, we proved that every idempotent of the quotient lifts to an idempotent of B. Okay? Good. So this proves by induction. So this has already fewer maximal ideals. So by induction, again, we prove the statement. Now let's prove that 4 implies 3. And this uses a non-trivial geometric ingredient, which is called main Zariski's theorem. Okay, that's the following innocently looking assertion. So you have, so it's, so let x be, well, x to y be a quasi-finite, separated morphism and y quasi-compact. So what is a quasi-finite morphism? Свои конечные. What are examples of quasi-finite morphisms which are not finite? Открытое вложение. Теорема Зариска говорит, что ничего другого не бывает. Then there exists x prime. This is open, and this is finite. Well, so let me see if I can erase here. Yeah, I can erase. So we are going to apply this to the case when y is affine, and actually in our application x is also going to be affine. And in this case, you can produce, in general, you can produce x prime explicitly. So if x is spec B and y is spec A, then we can take for x prime spec B prime, where B prime is the integral closure, normalization. B prime is set of all elements B in B such that B is integral over A. So not every x prime has is necessarily of this type, but if you require x prime to be normal, then you must define it by this property. So so the claim is that for affine schemes, this construction works. And what is the main point here? The main point is that this is, with this definition, this is an open embedding. It requires a proof. It's not obvious. So that's what I will use. Now let's see. So let's apply this. So okay. So that's the statement. So now I have diagram spec B, spec A, and this is spec A. So this is etal. So I have this map, and now I use main Zariski theorem to embed it. It's an open subset of something finite. And this is finite. And this is open. So now I can decompose these guys into disjoint union, into product of, into disjoint union product, in disjoint union of spec B I by property 4. This is 4. And so this I corresponds to maximal ideals in B prime. So that's just localization with respect to maximal ideals. So assume, say that, so I have spec A. It's a closed point in spec B. So in particular, it gives me one of the maximal ideals here. So let's assume that spec A, this point, lands into spec B1, right? Choose I such that this is true. I choose I equal. Yes, that's this map. So then we have the following diagram. Well, so let's see here. So this is open here, and it intersects spec B1 prime. So that means that spec B1 prime actually sits inside spec B, right? Because spec B contains this spec K, and this is open. And what else I need to say? Do I have to find it? Just 1 second. So I need to say that my B, right, and this is local. Right? So why is it true? Just because one point, this spec A, sits inside one point here, sits inside spec B. And on the other hand, spec B is an open subset here. So that means that spec B contains an open neighborhood of this point. But this is a local ring. So if closed point belongs to open subset, then the entire spectrum of this local ring belongs, right? So in particular, what we have is that, so now we arrive to the following diagram. We have spec K. We have spec A. And here I have spec B1 prime. This is open subset in spec B. So I have this. I have this. And I have this. So what do we know about all these maps? We know that this is finite, because this is finite and this is one connected component. I know that this is a tal. This is an open embedding, so that means that this is finite et al. And finally, it induces isomorphism on its fiber. The fiber of this map over B prime 1 modulo maximal ideal is just 1 point, because it's still here. Right? So it means that this map is an isomorphism. I have a finite étale map whose fiber, such that if I take the fiber of the closed point, it will be, well, it will be an isomorphism. Right? That means that B prime 1 as an A module is free of rank 1. It's a finitely generated, it's a free module, because finite étale, so it's flat, so it's finitely generated free module, and modulo the maximal ideal is generated by one element. It means that this is an isomorphism. Agree? And this gives me a section. So now let's see what else we have to show. I have to show that 4 implies 2, and that's so 4 implies 2. Okay. So take for B A of t modulo f of t, and then so I have B modulo the maximal ideal, the fiber. So this f factors modulo the maximal ideal into product of relatively prime polynomials. So I can write this as product of k of t modulo G0 times k of t modulo H0. Now I have B mapping here. And so we already know 4. So 4 tells me that connected components of the spectrum of this guy are in one-to-one correspondence with connected components of the spectrum of this guy. And in particular, here I have a factorization. So, right, it means that I write the spectrum as a union of 2, well, not necessarily connected components, but 2 disjoint open closed subsets. So this gives me a factorization of this B. So B1, B2. That's unique, such that this reduces to this and this reduces to this. Now, what do we know about B1 and B2? Well, they generated by BI is generated by one element. They generate these algebras as A modules. They're generated by, well, as algebra, they're generated still by this one element T. And that means that I can write each of these is A of t modulo some g. And moreover, so if say degree of G0 is equal to n, this guy is generated by 1 t squared t to the n minus 1. It means that by Nakayama lemma, this guy is also generated by 1 t to the n minus 1. So that means that I can choose for G polynomial of the same degree. So this is B, this is A of t modulo h. So here G and H monic, and degree G is equal to degree G0, degree H is equal to degree H0. And also the G is equal to G0, and H is equal to H0. That's because you have this map. And now this implies that the fact that, so now remember that B is this, so it means, so this B is decomposed as the product. It means that if the G times H, which is definitely 0, right? G times H, which this is an element here, but it goes to 0 in this product. It means that it must be 0 here, so it means that it's divisible by F. But these polynomials have the same degree, and they're monic, so it means that F is equal to GH. Okay, now done. So, and now let me, it remains to show that, so we proved that 2, 3, and 4, well, 2, 3, and 4 are equivalent. So it remains to prove, for example, that 1 implies 3. So 1 implies 3. And this is easy once you know a structural theorem for étale maps. Since it's useful anyway, I will. So prove that 1 implies 3. So here is the structure theorem. I need a definition. So let's say that a map from A to B, a map of rings, is standard étale. If B is of the following form. You take polynomials and you mod it out by some f of t, right? And then I allow to take and localize it, g of t. So, okay, so we're with g prime with f prime of t, invertible in B. Okay? And then there is a theorem, which is a structural theorem for étale maps, that A, So theorem is that map from A to B is étal. If it's locally, find standard étal. If étal at if for any prime in B prime there exists G in B such that the localization, such that G is not in B, and the localization B G is standard étal. Okay, so clearly standard étal maps are étal, right? So by ну, да, ну А сюда отображается. Да. Сейчас, в обратную сторону. Ага. Ага. So, again, so these are all these examples of étal maps, and the claim is that locally any étal map is of this form. So in our kind of definition of étal maps, we allow to have many variables, not just one, but it turns out that it suffices to consider just one variable with the expense of this additional localization. So once you have this theorem, well, 3 follows immediately because it suffices to consider B of that special form where its amounts follows from A, from 1. Okay. So this 1. Okay. So 1 implies 3. That will make no comments here. Okay.
What proves that 3 implies anything?
3 implies
Here's the diagram. We have proved these 1, 2, 3, 4 arrows, and this arrow is obvious, but we have not proved that 3 implies anything.
we don't.
2, 3, and 4 are equivalent, and then it's clear that well, 1 follows from 2.
Это мало. У нас из 3 вообще нет больше.
А, да?
No, okay. So clearly, if you have a picture like this, like in 1, right? So you just take A of t mod f, and then after localization, you get a standard étal map. So the fact that 1 follows from 3 is obvious.
But 1 implies 2 is still not.
Yeah, but I think now we proved everything. So you're right that this is so 1 is equivalent to 3. So one implication that 3 implies 1 is clear. For the other implication, you need this structure theorem. Now. Is now our proof complete?
No, we don't have that either 1 of 1 or 3 implies something of 2, 4. We don't have this error.
Нет, то, что вот из одного следует 2, это несколько утомительно. А мы, значит, мы не доказали 2 ни при каких... Сейчас.
1 и 3 это одно и то же. 2 и 4 это...
Хорошо, да. Но, значит, не все доказали, но я больше...
Второго очевидно следует первого.
Да, да.
Наоборот. То есть 1 или 3 следует 2 или 4.
Сейчас, ну давайте все-таки посмотрим. Значит, мы доказали 2, мы вывели 2 из 4. 2 из 4. Значит, мы, если у нас есть... Сейчас... Да, наверное, мы не все доказали, но давайте тем не менее, я хочу двигаться дальше. Надо было бы еще... Я думаю, что я... Ну, в общем, в любом случае, сейчас время подошло к концу, но я больше не хочу на этом.